So this last lecture is just about a few more advanced aspects, apart from the Basemap library, which is a useful library but rather specific one. Then there are some details about Python that may not be very useful in the beginning when you start with small programs or just trying to work something out. But then if you want to carry on and build something more complex or try to insert your own code into some other workflow, other software, something like that, there are some things that at least you should know they exist so that you are able to look them up and use them. So how to create your scripts so that they can read the command line arguments when you call them. These list comprehension generations are useful for some very common tasks of creating sets of values. Function closure is useful when you need to fit in your program with something that works differently and you need to create some functions to interface between the two. Classes are object factories. They produce objects, and so if you want to organize your code into object-oriented programming, you should know how to create them. And also you can overload the operators like multiplication and addition and so on in Python and can make some tasks easy. So I'm going to give some examples of these. These are probably not things you'll need right now, but if you carry on, it's useful to know that they exist, these examples. So let's start with this library. You don't have this library installed by default because it's about 300 megabytes or something like that, because it includes the coastlines for all the continents and the countries, the frontiers and so forth. But you can install this into Anaconda, and the usefulness of this library is to project geographic data onto maps. So let's start with this table of major earthquakes for the last 100 and something years. We can download this table from the URL there, and we can just read it simply. We can use pandas or CSV or something like that, but since we only need latitude, longitude, and magnitude, we can just read the file and extract the data from there and build a matrix like this. And now you need to install Basemap. So if you don't have it, here are some possibilities for installing. You can also install it with pip. So if you install with Conda, Conda is the package manager for Anaconda, and it installs in Anaconda. Some packages are not available in Conda. You can install them with pip, but then you just need to make sure that you are installing into the Python installation of Anaconda and not other version of Python you may have. So one way of doing that is running the Anaconda console that you have. If you install in Windows, you should have there, and then use the pip installation instructions from that. In any case, this is a toolkit for the matplotlib, and it includes this class Basemap that can compute the projection between longitude and latitude coordinates into the map, depending on the kind of map that we use. So, for example, we're going to use this multi projection here. So we set the projection type for the class. This is the central line for this projection. So we're going to center it at longitude 0, and the resolution is you have coarse, medium, high, very high, and this is the resolution for the coastlines, the rivers, and so on. In this case, since we're going to plot the whole world, we can use a coarse resolution because the scale is not, we are not zooming in too much. And then we have these methods, for example, draw coastlines, draw countries, the frontiers, fill the continents with some color, and so on. So we can create, draw the meridians, the parallels, and so forth. So this we can use to generate the map and draw these lines. And then we can just plot our data. So we're going to use this scatter plot. The x and y values are the latitude and longitude, and then which we specify here that they are latitude and longitude. So the object will project these into the projection that we chose. and we are going to set the size of the circle to 4 raised to the magnitude of the earthquake. So the magnitude of the earthquake is a logarithmic scale, and so to get a more or less a representation that is proportional to the actual energy of the earthquake, we can use a power scale here. And this is the result that we have. Larger circles are bigger earthquakes, smaller circles are weaker earthquakes, and we have them plotted on the globe. We can do this with other projections. For example, this site has a list of seismic events occurring in the last, say, 48 hours or something like that, near Portugal. And we can download this and plot, and we can update the plot if we automate this. So we can get this from we just download the page as we did in many examples. We have the values there for the latitude, longitude, depth and magnitude of the different seismic events. And so we can download the page, parse the data here. We can use Beautiful Soup and find the table that has the seismic event, and then retrieve the latitude, longitude and magnitude for all the seismic events. The trick here is that since this is in Portuguese, we have a comma separating the decimal point, so we need to replace that with a period before converting into floating points. But this is basically the same thing that we saw several times so far. In this case, I'm using Beautiful Soup to parse the HTML, finding the table, the rows and the cells on the table, and then I take the values from the cells that I want and create a NumPy array, a matrix with latitude, longitude and magnitude. And now I do basically the same thing, only in this case I'm going to use this Lambert conformal conic projection, which is more useful for regional plots, so I'm not plotting for the whole world, just around Portugal. I specify the width and height in meters of the region I'm plotting in the map, and the resolution for the coastline, and the latitude and longitude of the center of the plot that I'm doing. Then I draw the coastlines, fill the continents, and so on. So this is basically how you can use this Basemap class. You specify the kind of projection. For different projections, you may have different parameters to specify where the map is located, and then you have these methods for drawing the actual map from the database that it has on the coastlines and so on. And now we can plot again our seismic events, the same thing, and this will now be projected into this particular map. So we don't worry about doing the projections ourselves. We just use latitude and longitude, and the map object does all the computations, and we have this projection here with the seismic event. If we couple these two things, downloading the data and plotting, every time we run the script, it will give us the updated map of the latest seismic event. Another thing that we can use is to overlay the projection that we have with, for example, a satellite image. So this was an example from Susana Noronha. She was studying erosion on the Bay of Seychelles, and she had some stakes buried in the sand at some locations, and she was measuring over the months whether the sand was decreasing or increasing. So she wanted to plot the locations of her rods, of the measuring rods, using GPS. She knew the GPS location, wanted to plot them on the map. So she had the GPS coordinates for all of them, and what we need here is to use the satellite image from the region. We can obtain that from Google Maps, for example. And then what we need is to have some reference points that we can use to match the image with the map location. So this is a part that takes a bit of tinkering with, but eventually we can use the same projection, the Lambert conformal conical, but we just have to be careful to specify the reference point for the map that is going to be overlaid on the image. and also the scale, but this we can measure from the Google Maps image. We can measure distances and coordinates, so it's not hard to do this because we have all the data on Google Maps that we can use. And now we just plot the same thing, plot the data there, and we have this result here. So these are the locations for the stakes that were buried there. So basically with Basemap you have all the information for drawing countries, for drawing the continents and so on. This is useful if you're plotting large-scale geographic data. But you can also, since you can specify the projections and the exact locations for the map, you can also align this with satellite images or images taken, aerial photographs or something like that, and then represent your data there. So this is something that it's only useful if you're dealing with geographic data, but if you're dealing with geographic data, this makes a lot of tasks for representing your data much easier to achieve. Another useful thing is to allow your script to be run without changing the code in the script, or without you needing Spider or something like that. This allows you to insert your scripts into some workflow where you use some program to process something and then use your script and then something else. And for that, you need your scripts to be able to read command line arguments so that you can give the necessary information for a configuration file or data file or whatever you need your script to know. So let's go back to the tuberculosis plot we saw in the first day, and we're going to modify that script so that we can run it with these command line arguments, the three-letter code for the country, the input file, the CSV with all the data, and the output file, the image that the script is to generate. To do that, we can create this new script. So this will be, we don't have to change the other one we created before, but from the other, the TB plot one, the original one, we're going to import the functions to load data and to plot a given country. So this is the whole script we are using here. We just import from the other one whatever we need. We're also going to use this argparse module because this can give us a parser for the command line arguments, and we can specify which are the arguments that we want. So this is the label, the name for the argument, which we can use to access whatever the user gives us. This is the order in which they will appear, and we can also include documentation. So, for example, if someone goes to the DOS console or the command line, the whatever system you use, and they call Python and the script. So this is what you do to run your script outside Spider. You use the interpreter and give it as an argument your script. Since this has the arguments are missing from our script, we get this help message, which includes the name of each argument and whatever we write here for documentation. So this can tell the user how to use our script if the arguments are missing. If we call our script, so call the interpreter to run our script, and we give these arguments here. PRT, which is the code for the country that we want, the name of the input file from which we're going to read the data, and the output, which is the image that it will generate. So when we do this, the execution does not stop, because when we tell the parser to parse the arguments, if the mandatory arguments are not present, the parser will print that help message and terminate the execution. But if the arguments are present, then we can access them as fields in the attributes in the parser object. So the argument that we called country is here in arg country, so the result of parsing our arguments. The argument that we call the input, output, all of these are here. So now we can load our data from the file specified in the input argument, and then create a plot to the output file with the country that is specified. These are the functions that we saw previously that were in that tuberculosis plot product. So this way you can, whatever script you create, you can put that script, write that script in a way or adapt it in order to be able to receive these command line arguments and then use the script even without looking at the source code or opening it in Spider. Okay, now let's see a useful trick for something that is very common that you need to do. You probably saw many examples of these so far in which we need to iterate through a series of values. We can use range or something like that. If you need to iterate through a set of specific values, for example, an exponential sequence of values, one way of doing this would be to create a list with all the values that you need and then iterate through the list. The problem with that is that you need to have everything in memory all at the same time. So if you want to do this with millions or hundreds of millions of values or something like that, it may get very heavy on require too much memory from your machine, and that may not work very well. So if you just want to look through the values and you don't need to store them all at the same time, you can create a generator function, which is a function that instead of having a return, because return terminates the function and returns the value, uses yield. Yield returns that value, but the function is still alive, and when someone calls for the next value, the function will continue from the yield point until it reaches the yield point again. So when we create this exponential function, we receive a base and a count that by default is 10. We can use this, for example, in a loop. So this will give us 10. That's the second argument that is missing there. We'll have a default value of 10, this parameter, and it will give us the first 10 powers of 2. And the way this is working is that it first calls the function. The function will use p, which is the base, and stop there. And then the loop will execute the block of code inside the for loop. So we'll have print of these two here. This end argument for print, by the way, is by default the end is a new line. So if you do several prints, the display will change the line for each print. But if you change this, in this case I put the end as a space, and it will print the value and followed by a space. So everything will be on the same line. And then it will go back to the loop and call the function again to get the next value. So in this case it will continue from yield. It will multiply p by the base, so multiply by 2, and then go back there and yield the new result. So now it's 4, it prints it, and then 8, 16, and so forth. So we can create a function that generates all the values that we want. We can iterate through them, but doesn't generate them in memory in one go. So we don't need to, if we need millions of these, we don't need to occupy memory with that. We just create a generator function, and it will loop through all the values. Another way of creating a generator is, this is a short notation for that, is to use these parentheses, and then the expression, the general notation for this is some expression for some variable in some iterable, something that you can iterate, optionally with some condition. If you put these in parentheses, this will create a generator function that will output the expression for all these values every time the condition is true. So let's say we want to look at all the powers of 2 up to 2 raised to 10 to the power of 10 that contain at least one digit that is the number 1. So we can do this, 2 raised to p goes from 1 to 10, but only if there is a 1 in the string representation of this number. And now we can loop through this expression here, and this will only give us 3 iterations, because there are only 3 of these numbers that meet the condition there. 4, and we get these 4 powers of 2 that have one digit 1 in the number. So basically, if you want to create a generator for a series of values, and you can specify in this way an expression, a loop, and a condition for each iteration of the loop, then you can just put it in parentheses and use it in a loop. Yes?
So, if I want random numbers, like I want to generate random numbers.
Well, for random numbers, you have actually, you don't really have random numbers in the computer, because the computer does not have an actual random number generator, unless you have some sophisticated electronics for that. But in general, there are pseudo-random series. So basically, there are series that give much oscillation in the numbers. But you have in NumPy, for example, you have a random module that you can just use those functions. So if you need random integers, you have one function for getting you a batch of random integers or floats or something like that. So generally you won't use that, but you can put there some call to another function. For example, for outputting random numbers, you can do it like this if you want to output them in a loop. But it's often better if you need a batch of a lot of random numbers. It's best that you call the function with, say, I want 1000, instead of calling the function 1000 times, because there are some optimizations for guaranteeing some statistical properties of the batch of numbers that you're asking for, and so it's better always, in that case, in that particular case, it's better to ask for the batch. Alternatively, you can do the same thing with square brackets. And in this case, instead of producing a generator function, that is something you can iterate, it will actually return the list. So it will create the explicit list of values here. So this is one practical notation for this kind of operation that we do a lot in lists, which is we have some set of values, we want to check something and then do some operation and put the result in a list. If you need to do that, you can just write it in a single line, the expression, the loop, and optionally the condition. The condition is optional, so if you don't want to impose the condition, you can omit the if there. So this is a list comprehension where you just put all the loops in the loop, the condition, and the expression in the same line. Another thing that you can do with Python is this function closure. I don't know if you remember from when I talked about the namespaces, there was that intermediate one between local and global, which we skipped because we weren't using that, and that is for function closure. Functions in Python are objects, and you can create them inside a function and return them as a value. So they work exactly as any other thing in Python. So you can have a function here that returns this result, for example, in this case, this result is a list. So this is an object, we add things to the list for the Fibonacci series, and we return the Fibonacci series with a list. But this function, Fibonacci here, is also an object. So if we call Fibonacci, we have the, for example, we can call the documentation, that list, that string describing how the function works, or which variables it has, or even refer to the object itself. For example, in this case, our variable f will also point to the same object in memory as the name Fibonacci. So actually f becomes the same function that now we can call and use it. So functions work as objects, as any other objects like lists and so on. So we can have a function that will return another function as a result. Let's see an example for seeing how we can apply this. Suppose that we have a plot function that receives some function of x, the x value, and then the file where it will export the plot. So it will create a figure, it will plot the x values on the x-axis and the y values on the result of calling the function with x, and then save the image. This is just a basic plotting function. Note that this func here is a function. So we're actually executing it. It's not a list or an array or something like that. It's a function, but functions are objects, so we can receive a function as an argument and then execute it inside the other function. But now suppose that we want to use this to plot a polynomial curve. We have a function to compute the value of the polynomial at any set of x values, but it also needs the coefficients for the polynomial, because to specify the polynomial you have to give the different coefficients so it can compute the curve. And so we cannot use this polyval function inside as an argument for this function, because then this will only call the function with the x values and will not have the c. So we cannot fit the two together in this way. This is a very simple example, so it's a toy example in this case, but this is something that can happen. You have something set up for working with functions in a particular way, and then you have over here a very useful function but doesn't really match what you require on the other side. So the way we can do this is by using closure, which is provide an environment where we create a function, but that function can also access values inside that closure. For example, we create this polyfunction function here that receives the coefficients of a polynomial and returns this poly function that is created inside this function here. And this poly simply returns the result of evaluating the polynomial x at point x using these coefficients, coefs. So what does this do in practice? This function, poly, will need to receive the x. But when it is executed, we'll look at the coefficients that were created, that were present there at the time it was created. So the value of that parameter there is kept alive in memory and is accessible from this function. So even though this function only receives x, it can still access the coefficients there. So how can we now fit the polyval function into this plotting function that we created? We can use this polyfunc function here with a set of coefficients. This one returns a function that only requires the x, because it has access to the coefficients we specified. When we create a new one, then this one is existing in a new space, and it has also access to its own coefficients. So f has access to one set of coefficients, g has access to another set of coefficients. But both of them only need the x value. So we can put them in this plot function and they will work. And we can do it like this, and we can plot the two polynomials, even though each of the function was created by setting those coefficients. So for this particular problem, this is a bit of a strange way of solving it, instead of just adding an argument to the plot function or something like that. But in practice, as you start building your tool set of functions to work with your problems, you may end up in one situation where changing everything that you already have would be quite a bother. And so in that case, there's this solution where you create an interface function here, let's say, that changes from one part to the other, and you can now fit the code together. Okay? So remember, you have this possibility of creating a function that returns another function, and the inner function has access to everything the outer function would be able to access, and that is kept alive in memory as long as the inner function exists. Okay? Now, one powerful thing about object-oriented programming is the ability to create your own objects. So far, we've been using objects like lists, strings, and so on. They have their own methods, but we haven't yet created objects. In theory, you don't really need to create objects to be able to do complex programs, because as long as you break everything down into functions, you can write a program as complex as you want. But creating objects are practical for encapsulating functionalities, code, and data that go together well, so that conceptually we can organize them in a particular way, and that makes it clearer for us how the program works and how it's structured. So the way you can create classes in Python. A class is an object that generates objects in Python. In fact, classes in other programming languages are not objects, so class is the blueprint for the object, so to speak, and the objects are the instances. But in Python, the class is not only the blueprint for the object it generates, but it's also an object in itself. But that's a bit confusing, but Python works like that. Everything are objects. But for creating the blueprint of an object, one very important method that you're going to create is this init method that is called whenever an object is going to be created by that class. And since this is a special method that the interpreter is expecting to find, it has 2 underscores in the beginning and 2 underscores in the end. This is part of the name. So in Python there are these special functions or methods that are not to be freely renamed, that the interpreter is expecting, and the convention is that they start and end with 2 underscores. All these functions that you create inside the class, that are methods for that class, will receive as the first argument a reference to the object that is using them. So whenever you use a method from an object, it will call the function giving the object as the first argument, so that the function knows which object is calling it. And this is done implicitly. For example, we can create an object of this myClass class, calling the name of the class and giving the value that is sent here, that is needed here. We don't give the self argument because the first argument is implicitly given by the interpreter with a reference to the object. So what this does is it creates the new object and calls the init method with that object as the first argument and the value we gave here as the second argument. And now it will create an attribute in the object that called it and set it to that value. This is what this init function does. So if we create this object and now call the printVal method, the printVal, what it does is it prints my value is and then the value that was stored. Note that printVal also receives a reference to the object so that it knows which object it is that it's printing. But when we call it, we don't give that reference, because whenever you call a method from an object, the interpreter implicitly places there as the first argument the reference to the object. So this is how all these methods work. Let's see an example where we can create an object to store fractions. So we have 2 integer numbers for the numerator and the denominator. We create a fraction by specifying the numerator and the denominator, and the init method here will set both values. And then we can have a function here, a method for the object that will simplify the fraction. So this is basically, we are iterating here, looking at the remainder of the division between the 2, and this is the algorithm to simplify the 2 fractions as long as they have this common divisor by the 2 numbers. We can then divide them both by the largest common divisor. So this is for simplifying the fraction. So we can create a fraction by specifying the numerator and the denominator here. If we don't specify it, it will assume that is 0 over 1. So this is a representation for 0 that we'll have. And we don't have to give the first argument. That is implicitly given as the reference to the object. And the object is created with these 2, numerator, denominator. Then we can simplify. We call the method here. And when we ask for the numerator and the denominator, now it's 1/5 because it resulted from simplifying 5 over 25. Now we can give a better representation of our object by creating this method which has 2 underscores, str 2 underscores. This is the method that is called by the print function for converting any object into a string so it can be printed out. And now we can create this method here, where we are going to return the string which has the numerator, and then a slash, and then the denominator. And now when we print our fraction, it will print like this. So we can control how our object is printed by creating that special method that print uses for creating the representation. So we start with this fraction, 5 over 25, we simplify, and when we print, we have 1 over 5. Another thing that we can do is that we can specify the methods used for sum, multiplication, and so on. For example, this one, 2 underscore add 2 underscore, is called whenever the interpreter encounters the plus operator between two operands. So it will call this method by giving one of the objects itself, calling the method, so that the self is implicitly given there, and giving the other object to which it's going to add. So we'll assume that both of these are fractions, and we're going to add the two fractions and output the result. So the result will be a new fraction that has as the numerator, the product of the numerator of one by the denominator of the other, plus the product of the numerator of the other by the denominator of the first one, and the denominator will be the product of the two denominators. This is how we add the two fractions. Now we simplify the result and we return that result. So this way we can create these two fractions and we can just add them and get the result. So this is 5 over 25 plus 3 over 5. This gives us 4 over 5. And now we created this class that includes methods for doing these operations, and so we can now do operations with our objects just by adding them or doing the same thing for multiplication and so forth. So these are examples of things that you can do in Python with objects. It's not only encapsulating the functions that you need to operate on the data that the object will keep. This makes it much easier to use that data. So instead of you having to use additional functions and things like that, they can be all organized inside the same object. And this is the basic idea for the object, is some natural set of data and functions that can operate on the data. But in Python it's also easy to overload these operators, addition, sum, division, and so forth, just by writing the right method there that will then be used when the interpreter encounters these operations. So basically with classes you can represent objects or generate objects that bring together data and your function. So whenever you can think of examples that data goes very well together with some specific functionalities, then it's useful to write them as classes and have all the objects share these functions. This is especially important when you start having very complex code. In each case, for example, you can notice all these objects that you've been using for matrices, for example in pandas where you have a table and so forth. Having those methods that allow you to do things easily on your data is a lot simpler than just having a large set of functions that you can use. So whenever things start to get complicated and you see a natural candidate for bunching things together into an object, then it's good to build this fast. If you just do very simple scripts, small scripts for doing simple tasks with just a few functions, then there is no need to think about patterns. So this is more something of a long term if things start to get complicated. So to finish this part and the theoretical part of the course, some things here are a bit complicated that we saw over these 3 weeks. But the most important thing is that you know that these problems can be solved and there are tools that you can use. Even if the tools are not very obvious right at the beginning, but you know they're there and you can just explore, follow the thread here. I covered lots of different things because you come from different backgrounds and I cannot focus on any specific topic. But the idea is that all of you saw some things that can help you see the direction where you have to follow. So hopefully now you are more prepared to learn by yourself. It's the things that you need. or at least you have my email, so that could be one thing that you could use out of this course if you need. So just contact me and I can help.